Physics Part 185. Diffraction. At the end of section 8.5, you should be able to explain the meaning of the term diffraction. You should be able to show an understanding of the experiments which demonstrate diffraction, including the diffraction of water waves in a ripple tank with both a wide gap and a narrow gap. You should be able to recall and solve problems using the formula d sine theta is equal to n delta and describe the use of the diffraction grating to determine the wavelength of light. Although we often hear the statement light travels in the straight lines, there are occasions when this appears not to be the case. Newton tried to explain the fact that when the light travels through an aperture or passes the edge of an obstacle, it deviates from the straight on direction and appears to spread out. We have seen from the ripple tank demonstration, which is shown in the figure, that water waves spread out when they pass through an aperture. The effect is called diffraction. The fact that light undergoes diffraction is powerful evidence that light has wave properties. Newton's attempt to explain diffraction was not, in fact, based on the wave theory of light. The Dutch scientist Christian Huygens, a contemporary of Newton, favored the wave theory and used it to account for reflection, refraction, and diffraction. It was not until 1815 that the French scientist Augustin Fresnel developed the wave theory of light so as to explain diffraction in detail. The experiment illustrated in the figure showed that the degree to which the waves are diffracted depends upon the size of the obstacle or aperture and the wavelength of the wave. The greatest effect occurs when the wavelength is about the same size as the aperture. The wavelength of light is very small. Green light has wavelength of 5 × 10⁻⁻⁷ meter, and therefore diffraction effects can be difficult to detect. Huygens' explanation of diffraction. If we let a single drop of water fall into a ripple tank, it will create a circular wavefront which will spread outwards from the disturbance. Huygens put forward a wave theory of light which was based on the way in which circular wavefronts advance. He suggests that at any instant all points on a wavefront could be regarded as secondary disturbances, giving rise to their own outward spreading circular wavelets. The envelope or tangent curve of the wavefronts produced by the secondary sources gives the new position of the original wavefront. This construction is illustrated in the figure for a circular wavefront. Now think about a plain, straight wavefront. If the wavefront is restricted in any way, for example by passing through an aperture in the form of a slit, some of the wavelets making up the wavefront are removed, causing the edges of the wavefront to be curved. If the wavelength is small compared with the size of the aperture, the wavefronts which pass through the aperture show the curvature only at their ends, and the diffraction effect is relatively small. If the aperture is comparable with the wavelength, the diffracted wavefronts become circular, centered on the slit. Note that there is no change of the wavelength of the diffraction. This effect is illustrated in the figure. This is diffraction of the light at a single slit. Light leaving the single slit. Light intensity graph for single slit diffraction.